Hi, folks. Welcome to 1.4 Compositions of Functions. And so we're going to go ahead and start off this section with a what we know, all right? And the what we know covers the content from 1.1 and 1.2. And so far in this chapter, we've learned about multiple representations of relations, right? We've also talked about these relations maybe being functions and how to find out whether it is a function or not. Right. And in particular, we've also worked with how do we create these functions? How do we evaluate these different representations? And how do we find the domain and range for the multiple representations? All right. The last thing we talked about in 1.2 was something called piecewise functions. All right. So this is sort of a big picture of where we've been so far. And what's new for this section is we're going to be looking at combining functions. We're going to be looking at composing and decomposing functions. And we're also going to look at evaluating and determining the domain of something we call composite functions. Okay, so those are the things that by the end of this lesson, we should have a better idea of how to do these. All right, so let's get started. We're going to start here with combining functions with algebraic expressions. All right, now this phrase here, these algebraic expressions or operations, these are really referring to some things that I think are familiar to us, in particular, addition, subtraction, multiplication, and division. Okay, so we're not doing anything super fancy yet, but really just trying to say, what if we have a few functions? How can we add them, subtract them, multiply them, and divide them? Okay. So let's start with this example right here. Example 1 says, consider f of x equals x squared. Right, so let's go ahead and note that this is our f of x function is x squared. And then separately, we see that g of x is square root of x plus 1, right? Then the directions say combine the functions as noted and determine the domain of the resulting function, okay? So we're going to start first by remembering what it means to determine the domain from an equation. So that was something we learned in a previous section, okay? So to find the domain of f of x, right, that's our pink function. We want to find the domain of our f of x. What we need to think about is those clumping of the numbers, right? Like our positive numbers fine, our negative numbers fine, is 0 fine. Those are 3 pretty good groups to go with, okay? Now I notice that x squared doesn't have a fraction in it. It doesn't have a square root or any other sort of even root. And so that's why I can just say, okay, let me think about the positive numbers, 0 and negative numbers, okay? Now for the positive numbers, can I put a positive number into x squared? And will that be okay? And our answer is yes. Yes, we can square a positive number. All right, what about 0? Can we square 0? Yes, we can. And a negative number, can we square a negative number? Yes, we can. In fact, we know the square of a negative number is a positive number. So since we can plug in any number we want, we say that our domain is all real numbers. So from negative infinity all the way to infinity with the parentheses. Okay, so here we have our domain for f of x. All right, now we ask ourselves the same question, but looking at the g of x function. All right, so the g of x function is the square root of x plus 1. And so one thing I noticed right away is that we have an even root. Okay, meaning we have a square root. And so the even root means that we cannot have a number less than 0 that we take the square root of, okay? So algebraically, that means that this x plus 1, which is the thing inside the square root, right? This x plus 1, that can be greater than 0 or it can equal 0. And that's how we write x plus 1 is greater than or equal to 0. And if we subtract 1 from both sides, we get x is greater than or equal to -1. And when we want to write this as a domain, we say that we start at -1 and we include that. So we have a bracket, comma, every number bigger than that is fine. So -1 bracket, comma, infinity, parentheses. And this is our domain for our g of x, right? So we've got our g of x domain. We've got our f of x domain. All right, let's take a look at these algebraic operations now. Okay, so we're going to take a look at C. And letter C says, what happens when we add f plus g? All right, so f plus g means we grab our pink function, which is x squared, and to it we add our g of x, or square root of x plus 1. All right, now this is an x squared, this is inside of a square root, so I cannot combine that anymore. So even though it looks kind of weird, x squared plus the square root of x plus 1 is our function when we add them together, okay? Now that's the first part of our answer. The second part is we need to find the domain, all right? And it turns out that we have to look at the domain of both input pieces, all right? And so even though this one is all real numbers, in order to use the second function, we have to choose a number bigger than or equal to -1. So our domain is still including -1 all the way to infinity, okay? So we have to think about an x value that can go into all parts of this, not just some part. All right, let's take a look at letter D here. Looks very similar, except instead of f plus g, we have g minus f. So let's see what that gives us. G minus f is our g function minus our f function. Same thing, we cannot simplify those. We don't have any like terms, so that's as far as we can go. But also when we're thinking about our domain, we need something that we can put into both the x plus 1 in the square root and the x squared. And so our domain is still our bracket, -1 to infinity. All right, so has to be -1 or bigger, and then we can plug it in for all the places we see x. All right, let's move on to E and F. All right, so E looks at multiplying these two. And so if I multiply these two, I've got my f function times my g function, right? So this is my f function. This is my g function, and all I'm doing is multiplying them. And if I wanted to, I could really get rid of these parentheses. I could write it something more like x squared times the square root of x plus 1, okay? But either version, either this one or that one is just fine. Now, same thing, we got to find our domain, right? And our domain, thinking about this algebraically, we got to think of numbers that we can put in anywhere we see an x. And since we still have that x inside the square root, we have to say including -1, but any number bigger than that. So -1 to infinity. All right, let's take a look at f. F is f divided by g. That gives us x squared divided by the square root of x plus 1, right? So this was my g function. This was my f function over here, right? Now, I wanted to use this example because for two reasons. One, it's more interesting when we have a square root in the bottom, okay? One thing we might remember about the domain is this cannot equal 0. So it's okay to have a square root of 0, but the problem is we have square root in the bottom, in the denominator, and we cannot have 0 in the denominator, okay? So in terms of our domain, we do want to think about -1 to infinity, but this time we can't include -1 because then we'll get a 0 in the denominator. That's not okay. And we don't include infinity. Okay, so this time we're going to use, instead of a bracket, we use parentheses, -1 to infinity. Now, the other reason that I chose this example, and I'll go ahead and write this in the black here, is that some of us, maybe I'll squeeze this in down here, some of us might be a little uncomfortable that we have a square root in the bottom. So sort of depending on who your previous instructors were, some instructors are very picky and they don't like to have that square root of something in the bottom. And so just to remind us, we could get rid of that square root by doing something called rationalizing, where we multiply by a fancy way of saying 1. Okay, so this is really saying 1. And when I multiply by 1, I don't really change anything. But what it allows us to do is rewrite this. So I get x squared square root of x plus 1 all over x plus 1. Okay, let's move that over just a touch so we can see it better. All right. So it would be okay if you wrote your answer like this, but it is not really the extra work I'm looking for us to put in. Okay, there's nothing wrong with it, but I want to make sure, A, you show me how you get here. So it's not a magical step where we just happen to get there, but also I think it's actually easier if we leave it in this form to talk about the domain. Okay, so don't worry so much about rationalizing, but rather think about the concept here and how that changes the domain. Okay. All right, last but not least, what happens if we take the function g and we multiply it by itself? All right. So g times g means I have the square root of x plus 1 times the square root of x plus 1. And if we think about a multiplying something by itself twice, and the idea of the square root, turns out that the square root of something times the square root of something is just that something. Okay. Now, normally, if we were to look at the domain for this x plus 1, we could say that it's all real numbers. We can plug in any number we want for x, is going to be fine. But because of where we got this function from, we actually need to consider the domain of the functions that it came from. So our domain for this one is weirdly from -1 to infinity because of where we got our original parts from. Okay. All right, so let's zoom on out. We could see this whole question right here. All right, but this was a nice little review, hopefully, on what it means to add, subtract, multiply, and divide functions. All right. So now let's go ahead and we're going to move along to something called compositions of functions. All right, we're going to take a look at 2 examples here and then kind of see where this goes. All right, so example 2 says, consider the functions f of x equals x squared minus 1 and g of x equals 2x minus 3. And so this first one, f of 3, all that means is we're going to grab our f equation and everywhere we see the x, we're going to put a 3. Right? And I think in a previous video, I had used yellow for that. So everywhere I see the 3 or x, I'm going to put the 3. Okay. And so what does that give us? That gives us 3 squared minus 1. Right? And 3 squared is 9. 9 minus 1 will give us 8. All right. And so good chance to just practice plugging in numbers here, see where we go. All right. And let's take a look at question B here. Question B now asks us for g of 3. So everywhere I see x in the g equation, I have to put a 3. Okay. And so this is going to give me 2 times 3 minus 3. So that's 6 minus 3. G of 3 is 3. Okay. Now, I'm not sure we've seen this notation yet, but FG of 3 is really saying take f of 3 and multiplying it by g of 3, which happens to be the first two numbers that we found in part A and B. So f of 3 is 8 times g of 3 is 3. 8 times 3 gives us 24. Okay. Not too bad, right? Practicing that multiplication and evaluating. All right, so let's try the second column. You'll notice that I've only written one question here and then these are blank. That's because we're going to write those together. Make sure we really understand how to write this notation, okay? All right, so D should look familiar because it is saying find f of 3, which is what we did in part A, right? So f of 3, just to remind ourselves, we get 3 squared minus 1, which is really 9 minus 1, which gives us 8. That's the same as the previous one. But this time, instead of finding g of 3, I actually want us to find g of 8. All right. In other words, the number we got out, I want us to put into the other function. Right? So g of 8 would be 2 times 8 minus 3. That's 16 minus 3, which is 13. Okay. Now, what did we do in D and E? Well, we took a function, we plugged in a number, and then we took its output and we plugged it into a different function. So we didn't multiply like we did over in C, okay? And the way that we write this with math notation is we say, find f of 3. And once you find that, you put it in to the g function, okay? In other words, we found g of 8 to be 13. Okay. So this notation here, and let's get a nice color for this one. This notation is how we say take f of 3 and put that into the g function. Okay, so we put 3 into f, and then we take the output of this and we put it into g. All right, let's try one more example because I think that can be a little bit of a confusing concept, all right? So let's say we have this. Consider the functions f of x equals x over x plus 1 and g of x equals 9 minus x squared. So if we have -2 into the g function, that means everywhere we see an x, we're going to put a -2. So that gives me 9 minus, and I'm going to be super careful here, put in -2 in parentheses, because -2 is the quantity that I'm squaring, okay? So this is 9 minus -2 squared is 4. 9 minus 4 is 5. So g of -2 is 5. All right, well, let's find f of -2. All right, so f of -2, everywhere we see the x, we're going to replace that with a -2. So -2 over -2 plus 1, which equals -2 over -1, And a negative divided by a negative gives us a positive 2. All right. So we've got f of negative 2, g of negative 2, and now fg of negative 2, remember, that really says take f of negative 2 and then multiply it by g of negative 2, which will give us, let's see, 5 times 2, or 10. All right. So that's the way it would work if we were just multiplying. But again, we want to introduce this idea of putting the output into a different function. All right. So part D, same thing. We are going to plug in that negative 2 into the g function. So 9 minus negative 2 squared equals 9 minus 4. And that gives us 5. Okay. But this time, instead of saying f of negative 2, I want to do f of the output here, f of 5. All right, so f of 5 equals 5 over 5 plus 1. And from there, we get 5 over 6. Do not turn this into a decimal. Leave it as a fraction, okay? So 5/6 is our f of 5 value, all right? Now let's see what we did here, all right? We put negative 2 into the g, and then we got a number out. And then we took that output and put it into the other function. That's where that 5 and that 5 came from, okay? So how do we write this using this notation? We got to think about which function we put into which equation, right? So in this case, I took the g of negative 2 and I put it inside the f. So I'm going to have g of negative 2, and that whole thing I'm going to put into f. This is the same thing as saying f of 5, which equals 5/6. All right, so f of 5 and g of negative 2, that's what we put into the other function, right? All right, this seems like a good place to stop this first video. Come on back for part 2.